Okay, welcome back, everybody. It's time to start this new lecture. Today we are going to talk about SLAM with known correspondences. I'm going to explain a little later in case that, well, we'll need to do like some initial introductions just to make the problem treatable. Again, this is going to be the first approach to SLAM. There's many, the literature goes deep, but today we are going to start with the canonical problem of SLAM, right? What we discussed last day, it was the particle filter, right? So I'm just here writing these equations that at the end, this is what the filter looks like. If you remember, we derived this from the base filter. Right? And then with some slight changes with the initial derivation of the base filter, we obtained this form, right? So in this first equation, we were sampling on the motion model. This was equivalent to the propagation step in other filtering algorithms that we've seen. And this second step, which was related to the weights of our particle set, was actually correction, right? And then we talk a lot about important sampling, how these, let's say, sets of particles were actually representative of our posterior distribution or our belief just by reassigning these weights, right? Then what we do is we aggregate everything, and then there was this last step, which actually was like more implementation detail rather than a theoretical problem, right? Because theoretically, yes, if you have infinite samples, you don't care too much about this. You just have enough of them. But resample, what allows is with a limited budget of samples, we can still maintain like well, first of all, a representative set of particles, representative in the sense of the estimation that we want to do, right? Not like we don't have particles like in places where probability is low, but we want to estimate, we want to have particles where the probabilities are high. And then there was also this problem of the diversity, right, on the wave we were sampling. So that's why we defined like two approaches, right? One was independent sampling, and the other was the minimum variance resampling. Okay, so that was it. We didn't explain anything new because it's basically like a variation of the base filter. But this was a totally different thing in the sense that now we were allowing for any kind of distribution. So here you are not limited of, let's say, first order approximation and priors to be Gaussian. You could have here anything. The same goes for the priors, right? So this was a little more flexible, and then we also discussed that we basically need to propagate these particles, each of them, and then we need to calculate this likelihood function for each of them again. So this can be a little intense in terms of calculation. And then, well, what is the number of particles? This basically depends on the dimensionality of your problem. So for low dimensional problems like localization into D, it's a problem that it's fantastic for this kind of algorithm. For other problems, higher dimensional, it might not be that good, right? So this is a tool that it's useful, but you need to know well when to apply this. Okay, yes. I think this question is going to be answered on the break or after class, because this is related to the previous class. I was thinking, how is it possible that we spend so much time in classes? And I think the answer is your questions. They are very welcome. I really like your questions, but this simply makes our like prediction of how much time we spend in class just a little more. So please ask questions. Sometimes on the videos I was checking today, and yes, I hear them now, but then on the video you don't hear anything. You just see someone there standing very still. So maybe I'm just going to repeat. If I don't, ask me to repeat questions when you do it, right? So this question later, because this is from previous class. Let's keep our budget for questions just on today's class. Okay? Yeah, before we move on, there's a task that you have to do. Each of you, by the end of this week, should send me like a provisional, I mean, basically you need to send me like a list of people in your group, right, for the final project. So either like 2 or 3 colleagues, or I think ideally it was 3 to 5 people for final project. If you have only 2, if you have 1, we will try to rearrange groups a little, but I think at this stage we should start like grouping everyone together, right? So by the end of the week, you should have like sent like a proposal of these group members. We will also help if there's like necessity for, you know, TAs and me will be like a hub, right? If we need to put in contact like groups that are not like on the right size. But, well, you have time. I guess some of you have doing other courses together, so you might be familiar. But if you are not, still, contact us, and then we will make all groups together. Groups of 1 people or 2 people, that's not good. 3, it's borderline. Ideally, I would say that it's 4 to 5. Okay, yeah, a second thing, not related before we start talking about material. Problem set 1, it's almost close to be finished, right? All grading. There's an important thing. You should follow the instructions. So not many of you submitted a PDF and then a zip, right? What you did is some of you created like some Jupyter notebooks, put it on a zip, some PDFs and some code, if you put it everything on a zip. Why I'm asking this? Because if you submit a PDF and then another file, it's going to be easier for us to correct. Right, so we'll have like on Canvas, like things nicely put, and well, I don't think it's really a difference for you submit 1 file or 2 files. So for next time, let's try to do this, right? Submit a PDF with whatever answers you have, and then whatever code you have in another zip. Okay, so let's talk now about this new topic. We are going to introduce SLAM, right? So let's see exactly what this means. I think I said this on first lecture, but SLAM stands for Simultaneous Localization and Mapping. We have defined on the previous 2 lectures what localization is. So basically, we are estimating this, right, where we are. In this case, this is a state variable a pose in 2D. And then what is mapping? We were using this term, M, which we know that it's the set of landmarks, right? So in this case, for the localization problem, they were given. Correspondences were also given, right? We knew like a lot on this problem, but basically for us, our map was this set of landmarks, which are like features in our environment, but with a location, right? So we have several of them, thousands, 3, doesn't matter, but we have a set of them, right? So this is our map. So we are going to continue with this idea, right? The same kind of representation for the map in the form of landmarks and position, right? So this is also the thing that we want to estimate. What is our current location? Well, not position, pose. Okay, and to show this, let me try the following example. So we are here in our initial pose, right? So the robot is here. Remember that this is sometimes assumed to be given, right? So we have a belief of what is the initial pose, but it might be not known, so then your belief will be, I don't know, a distribution over all your space or whatever. But usually this is given. And if you remember for problem set 1, this was the problem when we were executing a sequence of actions, right? So there was like some uncertainty associated with the initial our initial prior, and if we just execute these actions over time, and remember that this uncertainty was just growing, right? And actually this is growing unbounded. There's no information that we are adding. We were just executing actions, right? And this comes from this. Okay, if you want, let me write it better like this, right? So we were just executing this. So this is the only thing we had, like a motion model, right? We had a prior. We know what happens when we propagate these states, and basically this was growing under control, right? This is also called a dead reckoning problem, right? This is known from other domains like navigation with, with IMUs also, but it's basically the problem of you don't have any way of observe your state externally. You just have this, let's say, access to your actions, right? And this means that your error it's going to grow unless you do something, right? So this is very bad for us. For 2 iterations, you still have like a covariance that is good enough, but imagine if you keep doing like thousands of iterations, eventually you will get lost, right? So your state, it's going to be, it's going to be so uncertain that it's useless, right? So what can we do to solve this? Well, we discussed a little about localization, right? But in this case, localization assumes that we have a set of landmarks that are known. But now imagine that we don't have this kind of information. We don't know anything about that. We just want to recover our position, our pose, as accurate as possible. And then what we are going to do is use all the resources that we have available in our environment. And in this case, landmarks are going to be one of them. So imagine we have this landmark 1. We don't know where it is, right? Initially, we don't know where it is. We are just observing it from x1. Okay? And then why do we want to estimate also this landmark? Because it turns out that actually this landmark is also observable. You can also observe this from your next pose, right? And to this landmark, there's going to be associated a covariance. And if you use both observations, both the transition function and the observation model, one saying that you're executing an action and the other you are observing the same landmark, basically this reduces your covariance, right? I'm just here, you need to believe me that this covariance is going to be smaller. But in general, you know about this, right? When we add observations, basically we are more certain. Covariances are smaller. So this is just for one of them. But now imagine that you also observe this like in many future state, well, basically in the following states of your system, right? You keep observing this landmark, so that means that your covariance is going to decrease also, right? So this is still not perfect. We don't have the same uncertainty that we had at the initial belief, but basically this intermediate landmark, it's like adding these observations that we need in order to decrease covariances. Remember that this is not known. This is not a point, right? Here there's going to be a covariance as well. But we are going to see what can we do to estimate this covariance, and actually this observation is going to reduce our next covariances on states, right? So now, instead of having one covariance, one landmark, we have another one, right? And basically, this is the idea. You observe enough of them until covariances in your localization decreases, right? So the only overhead of this is that we also need to estimate where these landmarks are. Okay, so eventually, if you don't have like good enough landmarks, this error can still grow like unbounded, but you can always relate covariances, right, through these intermediate state variables, which are going to be our landmarks now. Please, we have a question. Yeah, exactly. No, here what you have is a distribution of these landmarks, right, based on this, more or less. No. No. So it's not a difference between landmarks being static and landmarks being dynamic now. The difference is that this is what we had before. Imagine we have a delta, right, as our distribution. So this simply means that you have perfect information on this landmark. This is a localization problem. If you want to think on a probabilistic way, right? Now what you have is just an estimate of this. And we are going to discuss today how to obtain this estimate as you observe. So at the beginning, you don't know anything about this landmark. You just observe it, right? And then you start doing the estimation. And actually, as you observe this in many other positions, this estimation is also going to improve, right? So that's why this problem is called simultaneous localization and mapping. It's not just useful to calculate better your position, your pose, which is the localization problem. This also decreases the uncertainty on your landmarks. Right. You do a joint optimization of everything, and then, well, you are a little more robust to this dead reckoning problem. Okay, so this is the idea. We are going to be discussing exclusively about this. So how we introduce like landmarks, also to be estimated, how this affects the previous localization algorithm that we explained before. Can we use some of the things we did before? Or not, right? And well, basically that's it. And the first approach, well, you have guessed, but we are going to be doing also known correspondences. So there's going to be an association, an observation, right? And then we need to do the association. Is this landmark the observation that we are obtaining? It's the same problem as we had in localization. For now, let's assume that these correspondences are known. Right. Later, we will discuss how to do data association. But it's still the same problem. You cannot be sure that when you reobserve this is the same landmark, or maybe this is another landmark very close to it. Right. So how to distinguish between these? This is always problematic. Okay. So I'm going to start defining terms here. This is going to be given, right? So we are going to be conditioning, as always, with respect to a sequence of actions, right? Actions can be whatever. In case of problem set 2, these are the odometry measurements, but it could be anything else. And then we are going to have also a sequence of observations. Okay. And this is the new parts, right? So what we want to calculate is the following. We already discussed that, well, we want to estimate our position, right? But more generally, we can estimate like the full trajectory. So this is the sequence of all positions. We can call this a trajectory, right? And then our map, right? And we know that our map, it's simply this set of landmarks, right? In the two-dimensional case, looks like this. But the only difference is that now this is something that we want to calculate. Okay. Well, whatever number of, yes.
Should we add a signature also to this reference?
Could you repeat?
Should we add the signatures of the
Signature here.
to the map, the hamster?
No. No. Signatures, you mean, this is what we explained in lecture 5, when we were talking about what are these observations for the two-dimensional case, right? So it was a range, it was a bearing, and there was a signature, right? This is what you are talking about. No. Okay, maybe to do the correct data association inside of each landmark, you can also include like a signature if you want, right? But for now, we are going to be estimating just this position, right? This is going to help like another part of the problem, which is the data association. But for today, maps are just going to be this set of positions, right, of these landmarks. Yeah, but it's a good point. So if you were on the wild, if you were not giving all these correspondences, of course, you will need like some signature just to correspond observations and landmarks. Okay, so as I said, correspondences are given. So that's remember, this is the first entry to the SLAM problem. It can be much more complicated. But for now, let's start with known correspondences. And then there's a subtle detail, and that's why we start with these known correspondences, that if we add a single incorrect data association, right, then this can basically ruin the map. So it's not going to be possible for us to recover, depends on how much growing information we are adding to the state estimate. So this is going to be very sensitive, right? So let me write it here. Incorrect data association can ruin the map. So we need to be sure on the information we add to the system. If not, actually instead of adding more information, as we think that we are doing, right, with each observation, actually we are not doing that, right? Covariances are going to decrease, but this is an illusion. It's not for real. So it's not always the best thing to add everything you can, right? You need to be sure on what observations and what landmarks you are adding to your map. Okay, so then basically this problem it's recursive, right? So we have a map. We want to estimate this map, right? So with this map we can localize. And actually this map is going to be better estimated if we are well localized, right? So this is kind of a recursive problem. Where to start, right? Do we start calculating a map? Do we start calculating localization? We iterate. We'll see that actually this happens simultaneously, but this is kind of the egg and the chicken problem, right? What was first? You first localize and then you do your map, or the other way around, right? So this was localization, right? You have a map and then you localize. This was lecture 6 and 7. We didn't explain how to do mapping. We will do that, right? So if you know exactly your exact positions, you can still build a map. But this problem is a little more complicated, right? And I'm going to start with this, not just with the mapping, but the simultaneous localization and mapping, because the principles behind are like very natural. If we start describing the Kalman filter, the extended Kalman filter, Bayesian filter, for all these things, there's going to be a very straightforward solution that we'll see that we can apply here for this problem as well. Okay, so yes. It's known. Yes, for now. Okay, it's the same as with localization. We know correspondences. Okay, so what is the initial approach? Right? Why not? Let's start with Kalman filter, as I said. This is something that we know, we have been discussing during the last lectures. So use Kalman filter with known correspondences. Right? On the next lecture, I'm going to explain what to do with unknown correspondences. And also, let me write what is the graphical model out of this, right? So as always, we want to estimate this state from our previous, from an observation, and this comes after some action. Here, I'm going to write, well, I'm going to write it later. But not all states are observable, so our state xt are not observable. In general, we can only observe actions, right? And observations. And then we have an extra problem, which is now going to be, okay, so we have our map. I'm going to write in green, well, no, in blue, the nodes that we can actually observe. Right, just for you to remember that states are never directly observable. We always have an observation function. It might be trivial, it might be the identity, but still, the principle here is that we don't have direct access to this. And then, what is the thing that we want to estimate? Well, before it was this, just this position. But remember that our map was known. Now, in this case, we also want to estimate the map, right? So this is the graphical model, the resultant graphical model. It's going to be a chain. Still, Markovian properties are going to be used here, or we are going to assume that this system is Markovian. The graph, it's almost the same as before with the localization problem. The only slight difference is that now we have more states to estimate, right? So we have here a map that for now it's constant, right? It doesn't change over time. And then we have a position, right? After propagating the system, like giving some actions, and then we reduce uncertainty with time. So this is how the problem looks like. Okay? And yeah, oh, okay. Yeah, there's a minor comment here. Because here what I'm explaining, this is called online SLAM, right? What does this mean exactly? So what we're estimating is just, I mean, it's this graphical model. We are just estimating the last pose, last xt, and the map, right? And for this, we have all observations and all actions. So it's basically called online because we only care about the last state. If we assume Markovian properties, this is true. I mean, this is the most relevant state that we can estimate, the last one, right? Because the previous ones are not relevant. They are already included into this estimate. And there's a second kind of problem, which is called full SLAM, that it's going to be a little more interesting, right? So in this case, what we want to estimate is the full trajectory, all our states, the map, and we are going to be doing this also with respect to the actions that we have observed, this sequence of actions, and the sequence of observations. Okay, so this will be lecture 10, maybe, right? I'm going to start describing, like, these are also called batch approaches, where we have, like, basically our state vector to be, like, everything. We are not here like doing any recursive estimation, which is filtering, right? Or in terms of SLAM, we call this online SLAM versus full SLAM. Okay, so today it's going to be about online SLAM. We only care about now. We only care about where we are now. But this is still useful for some problems. Imagine you want to do an offline estimation, right? You have recorded your data, and then later you want to process this. So you don't want now to have an estimate of where you are, right? This on a filter way, but you want to estimate this later, right? So for that, you will just be, well, taking a full SLAM approach. Yes, you have a question? So your question is, we want, no, I'm just repeating. So we have here a joint distribution, right, which we still haven't discussed what it is exactly. And then what you are saying is what happens if we have a simpler distribution that we can factorize in, or not? That's not. Okay, so you are talking something like this, right? What if you don't estimate the joint distribution of x and m, but you just start with this? So this is localization. And then if you do the product roll on this, then later what you need to estimate is still, well, actually it will be the other way around, right? You will be doing factorization of m with respect to xt, and then here you will have just your map. This joint distribution always factorizes by the product rule into two distributions, right? So one can correspond to what is the best estimate of your map, or what is your best estimate of your localization. That's why here it's simply a choose, right? What are you conditioning against? You start with the map, you start with the localization, right? But no, the answer is you want to have the joint distribution of these two things, right? You don't want to start with one of them and then calculating the other separately. No, this is simultaneous. Simultaneously, you want to estimate both things, and actually this has advantages, right? Because the other is simply, it will be a different kind of problem. It's a different optimization process that you need to do if you separate them, right? So let's start with this. What we want is the joint distribution of both of them. Position and our map at the same time. There's not going to be like a division. Okay, so first we do localization and then we do the mapping. Okay, so I'm going to remove this. Okay, but everyone has clear what is the objective of today, right? It's this estimation of this joint probability. We want both things at the same time. The position, last position, or our state at time t, xt, and the map, right? These two things is what we want. So all our derivations are just going to be done to get these things together at the same time. Okay, so what is the first algorithm that comes to your mind if you want to do state estimation? EKF, right? So this is the simplest one. We know that it has some issues, especially with linearization errors and other things, but let's start with this, right? So this will be the straightforward approach to the SLAM problem as well. What means known correspondences, right? So we are going to have a set at each time of these correspondences. Remember that each observation, so this is equivalent to this, each observation is assigned to a landmark, right? So we have this for each instant of time, and just for abbreviation, let me write it this way, right? So this is going to be C of t. This is the set of all the correspondences. Okay, so if we do this, then this is going to be our distribution that we want to estimate. Again, joint distribution of last state plus all map. As I said, this is going to be given for now. Okay, and what else can we do? So I'm going to now define an augmented state. You can always do this for many other kind of problems, but in general, this is going to be useful in this problem, and you will see later why. So this augmented state, it's just going to be the both variables, right? The position and the map. So that means that we are going to have here this x, and then simply we are going to have like stack all the variables in all the variables that correspond, in this case, to the state of the map, landmarks, right, which are positions. So it's going to be 1, 2. Okay, and here I'm writing n. Okay, so, but you know that inside each of these variables are actually vectors as well for the two-dimensional case. This is small x, y, and theta, right? So this is our pose. And then these landmarks are going to be x and y. Okay, so nothing new. I guess if you are familiar with Python, you are tired of stacking vectors around and doing these kind of things. So it's the same thing. You have here a bunch of different elements. You just stack them into a column vector. Nothing strange so far, right? Now the price to pay is, so we have this, but we need to redefine now our transition function, and we need to redefine our observation function. Why? Because we have all these things, transition function especially, described for a robot state or a pose, right? We don't have these for landmarks, right? We don't know exactly what it is. And the same happens for observations. We are going to augment also the observations, and with that, it's going to be relating like not just states, but also landmarks. Okay. Okay, so far all these terms are just definitions. You should be familiar because we have been discussing like in all previous lectures, but now we have this new thing, right? This new augmented vector. So this is what we actually want, not just stacking a vector, but knowing exactly what is the distribution of this vector, right? We have argued that if we use EKF, prior it's Gaussian, we linearize function, that means that our belief it's always going to be Gaussian, right? Okay, so just by construction, we have here this stack vector. We can also say that this is a composition. This means it's going to be a composition of two parts. This mean corresponding to the robot. I'm just going to put it like x, well, robot or state. And then there's going to be a mean that corresponds to map. Okay, do you agree with me that we can do this? I think we did this already for conditioning and marginalizing the joint Gaussian. So it's the same. You just have here a vector. In this case, well, it's going to be convenient because we are stacking these two parts. And what else? And here we are going to have this covariance on map, and unfortunately, and I think this was your question, so can you have like a simpler factorization of these things? Short, no, because cross terms are not going to be zero, right? If they were zero, these two things will be independent, which is strange, right? Because we are talking all the time that they are very related, but then factorizations will be easier. So this joint distribution will just be the product of each of them. Problem solved. But they are not independent. So here we have these cross terms. Okay. So let's see a little more. What is the dimensionality of this? Because here it's important to know exactly what is the dimensionality of each of these parts. Let's go directly for the covariances. So now on this online SLAM problem, the state variable xt, it's just a pose, right? A position and an orientation, right? So that means that here we should have a block that is 3 by 3. Right? And then this other block, right, it's going to depend on the number of landmarks. And how many dimensions do we have per landmark for getting signature? 2, right? So here we have 2n, right? This is a square matrix, 2n, 2n. Right? So this is how this new covariance matrix is going to look like. We need to take this into account because now we need to calculate especially cross terms, right? We want to calculate them properly because if not, this fully Bayesian approach that we know that is the Stegner-Kalman filter is not going to work well. We need to give proper cross terms, and well, these are not going to be zero in general. Right? Okay, so it's going to look like this, 3 plus 2n, right? It's not that bad. Well, depends on n. But so far, we don't have like a lot. If you were working with, let's say, LiDAR data, maybe this number of landmarks is small because a two-dimensional range finder, which is this, well, two-dimensional LiDAR, basically, you don't have many features, so that means that landmarks are not going to be a lot. If you are working with an image, you're going to have a lot of landmarks there because you have a lot of key points, right? Maybe if you have a lot of texture. So this n, that might depend, but given the problem, this can be large or not that large. Okay, so now let's write this from lecture 4. Well, I don't remember lecture, but you also have a description of EKF-SLAM in Probabilistic Robotics book. I think it's all chapter 10. They explain SLAM with unknown correspondences and SLAM with unknown correspondences later, right? But if you want, you can take a look, right? So this will be an explanation, a great explanation, by the way, on each of these steps, but it's basically the equations that we are going to be explaining here, right? So just as a reminder what EKF looks like, it's going to be this. We have a transition function. Remember, this can be nonlinear. We have covariance after this covariance transformation. And these G's were Jacobians, right? The Jacobians are the derivative of this transition function. Right, so this is for prediction. I'm just going to put things because we always do the same, right? We write the algorithm, and then we need to identify which parts have changed with respect to previous EKFs that we have explained and are going to be new for this SLAM EKF. Okay, we have Kalman gain. Again, this Jacobian, we are going to be it's going to be defined later. This is covariance of the observation, but the inverse, and then here we have the corrected mean. Yeah, maybe I should just point this out. And finally, covariance. Okay, so it's going to be very simple. This is known formulas that we have discussed. Now let's go exactly to define each of them, right? We need to know exactly what is each of these transition functions, the observation function, and Jacobians. H? This? So what is H? H is the Jacobian of the observation function. So if you remember, we always have an observation function that is something like this, right? Can be nonlinear, whatever. And then well, basically the derivatives with respect to each of the components. Now with respect to y, this is going to be the Jacobian. Okay. Just as a reminder, we discussed last day, so what happens when we have multiple observations, right? And I think there was like this discussion, so we can do a batch update. That means you calculate Jacobians once on the same linearization point, which can be this, right, after propagation, and then you calculate whatever is the result, or you do this on an iterated way, right? You first estimate you do a correction for one observation, and then you do the following one, and then the linearization point has changed slightly, right? So these two approaches are different, but still the details are just on the linearization point. So here you could be using the same technique. If you want a batch update, fine. You go with the initial state, you linearize everything, and then you just do a summation. You want an iterated approach, you do this incrementally. So you estimate correction, covariance, and then your linearization point for the next update is going to be slightly different. Okay, so let's talk now about prediction. We have a question? No. Okay. How are we on time? Oh, we are good. So just as a, this is our augmented state, right? And now our transition function should look like this, right? So we need our previous state, and then we are going to have an action, right? And this is going to be, let's say, new transition function or transition function for the augmented state. Augmented. Okay. Okay, so this is what we want, right? If we want to just apply directly EKF, we need to have this function, which is relating our state, right? If it was like just relating X, that would be useless, because then how are we going to incorporate all the, I mean, basically these functions will not be correct. We need like an output of this function that is our state. So that's why we are augmenting. How to change this? Well, it's going to be simple. So, okay. So this is the first part of it. I'm just going to write it like again. This is just blocks in this vector. We know that this G, it should output full state, right? So that means that here, the first state, this is our old transition function, right? Can you allow me to do this, right? So this block of this part, it's just going to be our old transition function that we have explained, right? So this is just for 3 by 3 or whatever is your dimensionality of X. And then here, this is not going to change. So we are just going to have like same matrices, right? And then if you want, we can add some noise. Okay, in this case, this could be like the odometry model that we discussed, or a free moving point in 3D, whatever you want, right? As long as this corresponds with your state. And if you want to write this a little more compactly, at least for the odometry model, we know that this is going to look like this. So we are going to have our previous vector, no changes here. This was always true, right, for motion models that we described. Here we just have the previous state, and then we were adding a nonlinear term, right? So in this case, for the odometry model, it was something like this, the trans, and then there was a cosinus, and then we have the trans, sinus, and then we have the rotation of 2. Right, so this was explained last lecture, and then the interesting thing is that for this augmented state, all the other values of landmarks should not change. So here what we have is basically a bunch of zeros. Why is this? Because although we have an augmented state, our transition function, what it's telling us is how this is changed, how this state changes over time. So if we have this define a landmark to be a known position in the map, you apply any action you want, you are not going to change this position, right? Actions are, well, transition models. Of course, you can you can come with your hammer and just move the landmark, oops, or destroy it. But that's not the point. The point is that landmarks should be constant on time, right? So there's no transition function that is going to change this, right? So that's why we are writing here zeros. Yep. This is a very good point. This is just term that we are adding in order to be compliant with our previous definition. The trick here, it's going to be the covariance on the noise that we are adding. So you can imagine that if we are adding this is probably it's just formal, right, a way of augmenting the vector, but we need to make sure that every part of it corresponds to what we defined before. So covariances we'll see that are going to be almost trivial. Basically, we are not going to be adding noise because the covariance there is going to be 0, right? We are going to have blocks, but still with this we have exactly the same function as with the star. So we have some previous state, some action, some noise, and this is all we need for the EKF. Okay, so I think we can do a small break, 5 minutes, and then we'll get back. Okay, time to get back. So we were discussing on how we need to slightly modify the transition function in order to be compliant with a definition on the EKF, right? So in this case, we have just do this. If with the augmented vector was just stacking the state variable xt and then all landmarks, then the new transition function, it's going to look trivial, but actually there's like a lot of insight here. So this new transition function is our old transition function. This is changing the state of our, let's say, position. And then we have all other landmarks. And these landmarks are not going to change. There's no action here that we can execute that are going to change this. So this is done then. This is the first equation. This is just going to be evaluating this with respect to the previous estimate, right? And then executing action. Okay, so now a little more interesting. What happens with covariances, right? And this is equation number 2. What we know from the EKF is that we need something like this, right? So this covariance transformation, right, after doing the marginalization becomes something like this. We multiply on the left and right hand side of this prior covariance or belief of our previous state as this, and then here we are going to have some noise, right? So this is the covariance of noise. So if we have just described this new transition function, then let me write what is its Jacobian, right? So we have this, right? We have transition function depending on this augmented state, and then we need to derive with respect to this state variable, right? So that was the definition of the Jacobian. And remember that here on the EKF standard version, we choose just the mean, right? In this case, what we have is the mean of our previous belief. But okay, so I'm going to write exactly the definition of Jacobian, right? So each of the columns, it's going to be the derivative for each of the state variables. So here we have the x, the m, and then, well, the m by n, right? So this is just for you to remember. Gradients are transposed, by the way. So then, if we go element by element, what we are going to have here is this transition function on the state that we discussed on the previous lecture with respect to this x, right? So this term is known. This is the Jacobian that we described in lecture 5. But then let's discuss a little what is this, right? So we have the same transition function of our system, now with respect to a landmark, to the previous to the landmark number 1, right? So what is this going to be, right? We just need to think on the Jacobian. But here, if we derive this with respect to landmark 1, how is this affecting? How is this transition function being affected by this landmark? There's no relation, right? So then that means that our gradient is going to be 0. Okay, so this is true for well, this until you get here. So the only thing that it's going to change is the first subblock, right? This is our old Jacobian that we calculated, right? And then here we are going to have a bunch of zeros. Okay, so this is at least for the old transition function that we describe of a system, but now let's see what happens when we derive a landmark with respect to x, right, with respect to the pose of the robot. So that's also independent, right? So here we are not adding any dependency. This is not a function of the state, although for estimating this we need the state, right? So for now we are going to assume that this landmark is not related to the state when we are executing the transition function, right? So that means that this Jacobian is going to be 0, right? There's going to be like a lot of zeros here, and the only dependence is going to be when we derive with respect to ourselves, right? So here we're going to have, well, 0, and then this is the only part where we are going to have like something that is non-zero, right? So it's derived of f1 by 1, right? So what does this mean? That we have basically here a diagonal of zeros, a diagonal of identities, and then we have in all our covariance just zeros, right? What? Yes, yes, correct. So how can I write this? Like this, 2 by 2, and we know that this is going to be 3 by 3, right? So this is just on this problem, on the two-dimensional pose, this is 3. Okay, so we are just calculating gradients, nothing crazy here, but the fact is that if we don't have this new augmented state variable and this new augmented transition function, we cannot apply EKF. So far, these are just minor changes. Let me also write it this way, right? So we are going to have this g of x, we are going to have a lot of zeros, and then here we have an identity that is 2n by 2n, right? So this is all landmarks that we have here. Okay? Okay, that's great. If all functions were like this, almost trivial, we'll be like very, we'll finish classes very quickly. But next functions are not going to be that easy. Now let's discuss what happens with this new covariance on the noise, right? As we were, well, as you have already asked about it. So we have our previous covariance on the, this is the noise. This is epsilon that we are adding to the transition function. So every motion model has like some uncertainty associated here. That's why we have the previous R. But then what we are going to say is that landmarks, they don't get propagated. They are just the same. It doesn't matter what action you are executing. It doesn't matter how many actions you are executing it. It should always be whatever you have estimated, right? You shouldn't be changing that. So that means here that this covariance is going to be a very strange one, right? Where you have basically a bunch of zeros. And then the only, basically the rank of this is just going to be the dimensionality of your state variables, right? But we still need this, right? In order to write things on the, for the EKF. Now, I'm also here writing what happens when this noise is not in the state space, but this is in the action space. So we are going to have like this covariance, right? This is the Jacobian. P is the Jacobian. And then, well, for only the robot system, and then we have this. And then again, it's going to be a lot of zeros. So either if it's action space or state space, the covariance matrix of this noise, it's going to look like almost, I mean, empty, very empty, lots of zeros. Exactly. We are not adding noise in the propagation state. Noise is going to come from other sources, mainly from the observation function. But just what it means to propagate your state, here, there's nothing we can do. And why is that? The reason is landmarks are static. Doesn't matter doesn't matter what action we execute. It's not allowed to bring like a big hammer and hitting your, that will be like another kind of problem, which then makes things a little more interesting, right? So you have landmarks that change over time. So you can still have like other equations. But for this approach, our transition function is just treating them as static. Okay, and now let's take this. So instead of, you can redo this at home if you want, but instead of reformulating the Jacobian for with respect to the state variable, you calculate the Jacobian with respect to the action. And remember that this is around the error of the action, right? This is your B. B is the Jacobian with respect to the action. And this is what you need when you need to propagate noise out of the action space into the state space, right? So this is just a transformation that we explained the other day, but you can do exactly the same thing. Here, your Jacobian, it's going to look the same. You're going to have a BT here on this subblock, and then it's going to be the same for landmarks. So the derivative of landmarks with respect to the action, it's always going to be, no, actually no, you don't have the identity. You are going to have zeros, right? The derivative of landmarks with respect to the state, it's going to be 0 because they don't depend on the action. This is the only dependence on action, right? So but still you need this dimensionality. Basically your Jacobian has to have rows n, well no, 3 plus 2n in this particular case, and then the number of columns in this Jacobian is just going to be the dimensionality of your action, right? RT where? Here. 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 No, this is if you do the transformation. So remember that I was deriving like two things. One is action space, where I formulate noise this way. Right, and in this case epsilon, it was a normal variable. And then in the action space, we have a similar thing. Right, this is a different random variable, but the distribution of this random variable, it's this. Yeah. So it's not the same random variable. It's simply that one of them, you're applying it here directly to your action, and the other, this is a different configuration, it's directly on the action space. But they are equal because one is just, I mean, with this, you are just propagating this noise into the state space, right? So if you want to make things equal, RT should be equal to this propagation of Jacobians and the M matrix. Okay, again, I think for getting a little more intuition, let's plot exactly how this matrix looks like, what parts of this? Okay. Yeah, that's a bad thing about drawing, that I need a lot of space. Okay, so here we have our square matrix, right? I'm just going to write those terms that we have just updated, right? So if we execute this transformation, hold on, this transformation, we multiply the Jacobian by our previous covariance, right? And then we add this R matrix that we have discussed what it is. It's almost empty except for some blocks, right? These are the parts that are going to change, right? So here we have the new propagation of X. This is going to change for sure. We have cross terms. And here we have the covariance on landmarks. So I'm going to write with this color what things have changed. So of course, we have propagated after executing an action. These covariance should have changed, this block. These cross terms will also change. They will get updated. Right? And this cross term as well. So this is just a result of multiplying this Jacobian, which has like the identity, and then it has like a block matrix at the left upper corner, right? So this thing, right? Just with this term and then this identity, what it changes is the cross terms with respect to x. And what happens with the terms with respect to m? Do they get updated? Identity matrices, correct, yeah. So just given this structure of these matrices, then the covariances on landmarks doesn't get changed, right? So that's correct. We are not changing that. But this is, again, this makes sense with what we have described. So landmarks are static, actions don't change it. If they don't change the mean, they also shouldn't change the covariance, right? So we have the same estimation. Nothing has changed here. It's basically consistent. So mean stays the same, transition function treats them as constant, and then covariances keeps the same distribution. Okay, so you can go at home and then redo this or show that actually this thing never changed, right? So then you will be multiplying Jacobians. Remember that here what you have is this, right? So then you need to start with maybe something like this, and then do something like this. And then you have R. But, well, R, we know that it's only affecting this, right? Okay, so this is a good exercise, multiplying blocks. If not, it's fine. I think the idea is that only part of it is going to change. I'm also going to write now, according to probabilistic robotics, what is this covariance that they were using for propagation, right? So I think I didn't write this for the localization, so maybe it's a good time. And it's the same thing. They always do the same thing. They treat them as individual independent random variables, but the diagonal depend on each of the magnitude for these odometry values, right? So here we have this, plus here we have a 0. I think this is also in the probabilistic robotics book, if you want to take a look, right? But so what is the meaning of this? The meaning is, well, this noise is going to be independent. This is important, but basically the larger updates you do, the most count wheels you have, it's going to be more noisy. Right? So if you are moving very slowly, this covariance, it's not going to be, I mean, yeah, this uncertainty here on the motion model is not going to be a lot. If you move fast, that means that you have a lot of count wheels, then your uncertainty is going to grow, right? So this term is going to be bigger. Okay, so, well, you have this on notes if you want, but this is just a description. You could be using uniform identity as your covariance, right, as even more simpler approach. Or you could be using a very strange covariance that you have estimated after doing many thoughtful experiments, right, or algorithms where you have cross terms that are actually meaningful, and then you have a lot of statistical reasons, right, why to use this. So that's another option. Okay, so, oops. Now let's go to the second step, which is the correction step. And here we'll see that, well, we need to do a little more things. Actually, we are going to divide this in two steps. Basically, the first one is Oops. We have a new landmark. And that's something that we haven't discussed before. So what happens when your state space grows in the middle of your update, right? So Kalman filter is not really giving you a solution for that. It should be a little, well, we basically need to adapt some of the equations in order to apply EKF normally, but this can happen. So the world doesn't stop. If you see a new landmark that you want to add into your state variables, you are going to have more variables, but still, what can we do? And then the second step, it's going to be, well, we do correction, proper correction. So we observe landmarks, and then covariances are going to change, right? So both in our state and landmarks. Okay, so new landmark. How to initialize? I think this is the biggest problem. How to initialize it? So in this case, I'm not going to talk like in general of any observation function. In fact, this is not possible for all observation functions, but I'm going to be using the observation function that we described last day, right? And if you remember, it was this bearing and range thing, right? So here you see the landmark, and this is going to be R and local bearing. Right, so this was our observation, if you remember. Okay, so this is our function. It's still nonlinear. Let me write it. And now what I'm going to do is, so we have our augmented state, right? And here I'm just going to write that this is with respect to landmark J, right? We know we have correspondences, right? So this is another thing that we have here. Our C, it's just giving the correspondences. So this observation function is going to depend on two things. One is our state variable. Here we have pose and all landmarks, but what we need is which of these landmarks this observation corresponds to, right? So it's not enough to have all positions of landmarks. We need to know these observations to which landmark correspond, right? And well, here, yes, let me add some noise as always, because this is going to be, well, a probabilistic model. And well, these were the two measurements that we were interested. The first one is range, right? As I said here, this is range measurement, and then we forget about signature. For now, we don't care. So we need to calculate this range, how far this landmark is with respect to our local frame. And the second is the angle, right, with respect also to this local frame. So I'm using the same same quantities as we used before. This is distance. I'm also, just for later, this is going to be Q, right? These square terms, this difference. So you will see that this appears later in the derivatives. And then what we have is we need to calculate what is this phi variable. We know landmark. We know this position. So this is just applying this formula directly. Right, and then and this is important when you start implementing things for problem set 2. By the way, who has started problem set 2? Like, you have advanced a lot? Okay. A little? Okay, so it takes time to get used to the environment. But after that, I think it's just going to be applying, filling the files that are ready. But you should get used to the environment a little. So don't leave this for last minute. We are going to have like deadline moved a little, not for Friday, because Monday it's holidays here, right? So we must, but still, even if you have one extra day, please don't leave this for last day, because this problem set requires some time. And well, what I was saying is that this angle, if we calculate just this way, what we have is the angle in global coordinates, right? But actually what we want is just this, right? This is not this, so. And this is the orientation of our pose, right? So when we are seeing things in local frame, we need always to subtract the pose that we are observing, right? So if you imagine you observe this in your local frame, and it's not the same in your local frame, like, yeah, I'm watching here my students that are just in front of me, let's say angle is 0, right? But if I'm like in this other local frame, my local frame has changed, your position hasn't changed, but I'm not seeing the same 0 angle, right? It's going to be pi. So you always need to account for this. What is your local frame that you are getting these observations? So that's why we are adding here this, right? So this is the pose of the robot. So this is a little detail. Yes? Because this is already relative. This is the observation that you get. Range is not in global or local coordinates, right? So distance are just preserved with respect to any reference of frame. So you only care about this thing that you're observing here. But in this case, because this is in global frame and this is in global frame, the coordinates of our state and our landmarks are in global frame, if you calculate this angle would be this alpha that I'm writing here. This is not what you want. What you want is what you would be seeing like in the local frame of the robot, right? So angles are a little tricky. Yeah, maybe, so if you have gone on problem set 2, there's an explanation on these functions. So for now, we are gonna make them, I don't remember if it was minus pi and pi or 0 to 2 pi, right? But you always need to make sure that you are in this range. If you let this grow like, it's still valid, right? So this can be like any angle plus any multiple of 2 pi, right? Well, basically any angle is still the same angle if you add like 2 pi, but you will see later that you always want to be in the same range, especially when you apply Kalman gain. When you apply the Kalman gain, you need to be here. You need to be exactly on this range, because if you have this extra term that still gives you a valid angle, it's gonna it's gonna change slightly your solution, right? So basically you are gonna have here a bias. On problem set 2, it's a little more explained, but when you go there, you need to know that always try to do you need to think on what is the range of the angle. You cannot let this grow everywhere, right? This is especially critical when you do the Kalman gain. Any other place, it's fine to have any angle, but when you do multiplications, this is gonna be a technical detail that you need to solve. Yep. When you estimate your, so the question was if your state, this is in local or global, right? It's a good question. It's a very good question. So we are always going to be working on this global coordinate, right? So both our X and all landmarks are going to be in a global reference frame, right? It's the same frame for everyone. Now what happens is that what I have defined in the local frame are observations. So observations are always the result of a sensor. You cannot obtain a sensor already in a global frame. I mean, you can do that. That will be an awesome sensor. But usually they are like always referred to some reference of frame, which might not be what you want, right? Might not be this global frame. So that's why you need to transform these things slightly, because the observation you are calculating here with this given state and this landmark, what you should be seeing, this observation is going to be on the local map. So that's why you need to take this into account. Now we are introducing like frames on a very informal way, but later I'm going to introduce them more properly, right? So you will see this. For 3D, you cannot really do these kind of things. You need proper definition of transformation between frames, and this, well, this has to be exactly defined everywhere. This. No, that's not true. So you are saying why I'm subtracting the current orientation if this is already local? No, this is not local. So map, it's in global frame. This position of the robot, it's in the, no, this is global frame. This is global frame. Each of these differences are in the global frame, right? So then what you are going to be calculating, it's an angle in the global frame, right? You are going to be calculating this alpha that is here with respect to the x axis or whatever you have considered as axis. So you have an angle that is in the global frame, and you have another angle, which is your orientation, which is in the global frame. If you want to calculate this, which is the phi that we use in our observations, you need to do this subtraction. This way, it's on a local frame, right? But again, this is an informal way of transforming things. With 3D, we are going to be doing this more properly. Okay, so this is a technical detail that I'm sure you will be very proficient after doing problem set 2 or start doing. Most of the errors come from here, so Marcel can confirm this. You will see your estimation all of a sudden jumping. What's going on? Most likely it's going to be your orientation, right? You got your angle clip for whatever reason. You didn't project it to the 2 pi range again. And that caused like some trouble, right? So you need to think, you need to take care of this, right? At least consider. So when you see things like, oh, it just jumped, there's a problem on the orientation. It's a very, very common thing, especially when you start implementing. Okay, so this is just a reminder of lecture 5, right? Now, let's go to the point. So we were talking about how to add new landmarks. What can we do with this function? Not really much, right? Because this function, what it's saying is what you should be seeing. But what we want is the inverse. So we are going to be giving like some observations, and then we want to calculate what is the position of this landmark, right? So for that, let's define the inverse observation model. And this is for landmarks, for one landmark. Depending on your observation, maybe you don't have, the inverse doesn't exist. And then you need to find another way of initializing your landmarks. But in this case, there's an inverse exists, and actually it's going to be easier than the observation function. So imagine we get this, right? We want to calculate this chain new. This hasn't been in your augmented state. This is a new thing. But what happens is that we have obtained an observation, right? This is a new observation that doesn't match to any previous landmark. Yeah, for instance, you are here. This is your landmark 1. This is your landmark 2. And this is the observation that you get. Right? So you can say, okay, depending on how certain you are on your observations, this might be landmark 1, but depending on how you might want to say, no, this is a new landmark, right? Why not? At the beginning, how many landmarks do you think there's going to be? No landmark. At the beginning, you just have your state, your prior x0, right? So you need to incorporate these landmarks as you observe them. They are not going to be given. So what is the best way of adding them into your augmented state, well, we are just going to explain now. So we need this inverse function that, given an observation, in this case, this observation doesn't match to any of the landmarks. We have known correspondences. So you will know when this corresponds to a new landmark. Right? So we have this. And then what we have is the estimated augmented state. This is after propagation. So we have executed the action. And from this best estimate so far, this is the best we can estimate so far, with this new observation that for now I'm not entering on how we are deciding if this is a new landmark or not. Right? This is going to be a topic for next lecture. But for now, all of us agree that this, okay, if you want, let's do an even more strange one. Right? So this is M nu 2. This is clearly not what you should be seeing. Right? So we have good reasons to believe that this is a new landmark. Then what we need to do is create a new, we basically need to calculate what are the coordinates of this landmark. Right? So this is going to be easy. Remember, we have here range and bearing, and the inverse is just going to be give coordinates in global frame for this new landmark. So in this case, we have the estimation of, this is position, x and y. Right? If you want it this way. Like here. This is it. And now what we are going to add is just what we have is a range and a bearing. So just polar coordinates, and this is going to be where our new landmark is. Right? So here we have a cosinus of, this is the bearing that we're observing, and this is the estimated, this comes from the mu from here. This is our augmented state mean, best we can do, and then here we have a sinus. Okay, so this is the inverse. It just happens that this inverse exists, the inverse of this function, right? So one way is, okay, you have all coordinates, all positions, and you can calculate your range and bearing. The second is, given range and bearing, calculate coordinates, right? So this is even simpler, just, well, polar coordinates, and then you have it. Oops. Okay. And this is just a position. So everybody agrees. Now we actually have changed a lot of things because this hasn't happened before. We never augmented this state in the middle of an observation. But if you agree that this is our best estimate, and by the way, this is just going to be an estimate. We don't know for sure what is the right position because there's some uncertainty on your state variables, right? Especially on the position of the sensor. But still, this is a way for initializing it. So if we do that, then what we can write is our old augmented vector, right? It's going to be the same one plus this new landmark. Right? So the only thing we are doing is adding, stacking a new x and y for the new landmark. Okay? You have a question? This. Here. This is the position. This is corresponds to xt. Right? So this is the position of your robot or whatever. So observations are always centered in your sensor or your system or your robot, call it whatever you want. But in our case, this is a two-dimensional pose. So this is what we have. Where are the coordinates of this robot? And in this case, this is the x coordinate and this is the y coordinate. This. New 2. So why not? Yeah, so you can have one new landmark. You might have two new landmarks. It doesn't matter. The thing is that it's going to be like this. You are just going to stack them. as new, right? Okay, so we have augmented the augmented vector. No surprise, right? So I think this is reasonable thing to do, but then it's not so clear if we are initializing with this new landmark, what should be the covariance, right? Here, if we are calculating this on a probabilistic way, this is what we need for the EKF. It's not just, hold on a second. Yeah, it's not just augmenting the state and giving the new mean as we have calculated this new value, right? It's just, it's also about how to calculate what is the right covariance, right? And for that, what we are going to do is what we always do. We are going to do covariance transformation from our state variables to the new landmark that we have calculated. Okay, so this is basically the question. What happens with this new augmented covariance? This is how our old covariance look like, right? We had like a term of x, cross term of xm, cross term of covariances of the landmarks, right? We argue that this, we have discussed that these are the part that is actually updated, and on the propagation this doesn't change, but so far we don't care, right? But because what we have is this bar covariance. And now what we are going to do is augment this state. So if we augment this state, right, UT, it's this plus new landmark. So that means that the covariance should maintain the same dimensions, right? So if this has dimension whatever, this is the same, same dimension square matrix, right? So then we need to augment this thing, this covariance, in the following way, right? So then there's going to be this cross term, right, which is the cross term of this augmented state, let's say before augmentation, with respect to the landmark new. This is going to be the covariance of the new landmark, and then there's going to be this term. We know that this, because this is a covariance, this should be symmetric, right? But still, let me try it this way. New, and here y. Okay, so these are the new things that are going to be appearing here. Okay, so with this we'll have a covariance that makes sense, right? Now we have the more dimensions, but we need to change the covariance properly. So you could be putting here like anything you want, like zeros and whatever identity, but this will not be right, right? So we have discussed in many classes before what is the right way of doing covariance transformation, right? So we are just going to be doing the same thing. Okay, so basically the inverse is nonlinear. What do we do? Linearize. Excellent. It's almost instant that you should have this answer, right? You always try to linearize, see what happens, and at least for covariances, you will get like good enough estimation if the linearization error is not high enough. So covariance transformation. Okay, so this will be like more practice, but I think on this lecture on motion models, we already did this many, many times. So we have these dependencies, this inverse function, and then we are going to approximate this as always around the mean. And then let me write it this way. So now we are going to have a Jacobian with respect to the augmented variable, augmented state. Okay, I'm going to remove the bar here, but you know that It's, well, this is our best estimate so far. And then we are going to have another Jacobian, and in this case, this Jacobian is with respect to the observation. So, right? So this is the observation that we have. Let's say this is the real one, and this is a noisy one. We know that this difference, actually, it's going to be this noise, right? But we need to calculate this Jacobian. So let's get to it. It's always the same. The only thing is that, okay, we are explaining more Jacobians. There's more terms here, but it's always the same. So for when you describe a Jacobian, it should be instant. You get your function, whatever it is, and then you decide against what is the variable that you are differentiating against, right? So in this case, what should I be differentiating against? Y, yes. Linearization point, mean, right? Remember that what we have now is this bar, because this is just propagation. So this is it. This function actually only depends on xt, right? So I can write it without losing the meaning of well, basically in a more compact way, that this derivative with respect to all our augmented variables doesn't really depend on the previous landmarks, right? So you agree that we have a new landmark. This is not going to be depending on this. So this only depends on the state variable x, right? And here what we have is this. So there's going to be a bunch of zeros that I'm not writing, but you can imagine. It's simply adding whatever Jacobian I'm writing here plus all the zeros you want. Right? This is not going to affect. Actually, the zeros are not going to be changing much. The thing that actually it's going to change our covariance is this. So we start with this inverse function, derivative with respect to x, derivative with respect to y. Let me go again to the inverse, to this inverse function. So here we have x, and here we have y. Here we have this r, which later we'll see what it is, right? But this depends on the observation. And here we have angle, right? So the derivative with respect to x, there's nothing here on x except this term here. And there's nothing with respect to y except this term here. Here it was clear and mean because we were evaluating this at the mean. This is the best thing we can do, start evaluating at the mean. So this is going to look simple as this, right? Now the problem comes when we want to derive with respect to the orientation, right? So with respect to the orientation, yes. We need to derive the cosinus, so that's minus sinus. And then the same happens for the sinus, right? That becomes cosinus. Okay, so this is our Jacobian. We are going to see later how we use it. And this was basically thanks to this fact, right? So it doesn't, this inverse function doesn't depend on whatever landmark we have. It only depends on our current position. What is, yes, we have a question. You mean this step? Why are we using this? We are using this because if you do the derivative of this, then what you should be on the right-hand part of this is the derivative with respect to m1. And this we know it's 0. So here, from now on, what you have is a lot of zeros. 2n zeros. A lot of them. Right? So I'm just rewriting things to the significant parts that are not 0, right? So this L is just the Jacobian with respect to x because the others with respect to the landmarks are 0, right? So this is not going to change the result. You still have a bunch of zeros there that are not going to affect the cross terms, right? So for multiplicating this and getting these cross terms, yes, these zeros are going to be there, right? But it's simply not going to be useful at all, right? This doesn't add any information. But you are right in the sense that actually this Jacobian is much larger than this. So if we know that columns is each of the derivative for each of the variables, here it's not just x, y, and theta, but we have m1, m2, and whatever. Okay, so we have this Jacobian. Now let's talk about the Jacobian with respect to the observation. So it's the same thing again, right? We are going to be deriving with respect to z, and in this case z, it's a variable that just depends on range and b-ring, right? So it's going to be easy. So we go to the same nonlinear function, and then we start deriving with respect to, I always write it here, like on the bottom, just to have an idea. So you start systematically deriving all the equations, and then, well, you don't get mess, and things are more clear. So with respect to R was multiplying all these cosinus and sinus, so I'm just going to write them here. Okay, let me call this alpha. And then we have here alpha. And then derivative with respect to phi, to this b-ring. Okay. So we are just repeating the probabilistic model for any kind of nonlinear function that we explained in lecture 4. Now the only difference is that this now is the inverse. But again, we have Jacobians, we have a prior that is Gaussian. What is going to be the output? Well, it's going to be Gaussian, but the covariances are going to be depending on this. So for this, let's just derive it. So what is the right way of doing this? We start with the definition of covariance, right? So in this case, we want to calculate the covariance of this new landmark. Okay, so this is definition. For now, we have said, I mean, what is the best thing that we can say? That our mean was our observation, right? This is the only thing we can do. So if we come here to this expansion that we do here, and this is actually our mean, we write this, we write the mean, we subtract things, and then the only thing that remains in this difference here is the following, right? So here we have L with respect to delta x. I mean, I should be writing like x minus, I mean, whatever, but I think we're already like very familiar with this. And this is the difference in Z. We have said that this is noise, right? So this is the term that we have observed, but it's not really close to the reality. So this is the term in noise. It's going to be affected by this Jacobian with respect to Z. And the difference in your state, remember, here we don't care about previous m's, right? For this is 0. So you could also be writing this way. L, lots of zeros, right? It's being multiplied by delta x, m1, m2, whatever, right? So you see, you just do this multiplication, and then at the end what you get is L multiplied by delta x. Right? So that's why you don't care about these m's, because this Jacobian here is 0. Okay, and then we write the same thing on the right-hand side, but transposed. Okay, so many days doing expectations. I hope that by the end of this course you become the masters of this. But this is just the beginning. You could be doing like even more. Maybe it's not necessary. So today there are better ways, better things to do. Okay, no. So yeah, so we take out this well, we rearrange things, and we take out the constant terms, and then what we get as a result is this. So this is the block term in the covariance with respect to x, right? And here what we have, it's this. And Q, well, Q, if you remember, comes from the distribution of our noise, right? So every time that we have an observation, the noise affecting this observation is going to be this covariance matrix. This is given. It could be something that you get from probabilistic robotics, something that you just have calculated, but this is where, after taking into account these little noises. So that's why we need to propagate noise out of this, whatever inverse function it is, into our augmented state. So this is the way of doing this with Jacobians. There's always going to be Jacobians here doing transformations. Okay, so this is one result. More or less. What about the cross term? Cross term is not going to be, we wish it was trivial to calculate, but still we'll see that it's not going to be 0. So what's the reason for that? If it's 0, that means that your state and your new landmark are independent. And that's not true, right? They actually are very dependent. So we are just taking our position as given. We just do polar coordinates of our observations, and this is the first estimation of our landmark. So it's very, very dependent. This is the inverse function, right? So the inverse function here. What you need is this. So you have an observation, you transform this with whatever estimate, and the best thing you can do is estimate this for the mean, right? So, because this is not going to be a distribution. So far, we are calculating an exact number, our initial guess. And it's going to be very dependent. It's almost entirely defined by this position. So if we now put here covariances to be, cross covariances to be 0, then that's not good. We are doing, no, absolutely something not consistent. Okay, so let's calculate this. Just by the definition. This is the augmented vector, and here what we have is this difference in the new landmark. Okay, so I'm just going to rewrite things as I did before. Here, let me write this as delta y. Right? This is just the difference with respect to the mean and whatever perturbation we add. And here, this is the result from here, right? So m nu minus this mean. We know that it's going to be this inverse function that we have expanded with first order Taylor. So we get this thing here, and Jacobian with respect to the observation, right? It looks similar, but it's not exactly similar. And then delta y, actually, it's, if you know the augmented state, it's always, we have always defined it this way. So it's just state variable, x, plus all landmarks, right? But here, we also need, like, another consideration for this. Remember that it's going to be the same. Here the L, it was already containing a lot of zeros, but in this particular case, we have a question, right? Whether this noise on the observation is correlated to what things in this augmented state, right? And as always, noise, as we are considering here, it's only related to the state variable x, right? It's uncorrelated to all the landmarks. So landmarks are just static positions. They are not affecting noise. Imagine you have a camera. How can another landmark add noise to your observation, to your new observation that is totally far away, right? It could be, but no. I mean, usually they are not related, right? So then I'm going to write here that they are uncorrelated. This is an assumption we are doing, right? Right? So If we do this, if you do this later at home, you will see that here you divide things with respect to x and all landmarks. We are going to have here the block term that depends on x, right? And then here we are going to have exactly the cross term that we have calculated. Yeah. So this is the cross term that we get from the previous covariance, right? From our cross term relating all previous landmarks and the state variables. So if you remember from here, this thing, right? This cross term. So this cross term is just going to be multiplied by L T transpose. And we know that if this is a covariance, and we are now calculating this term and this term, they are going to be the same by translated. Okay, so we are almost close to derive this new, what is the new covariance after adding a new landmark. Lots of cross terms, lots of correlations. This is also going to give you like some hints of what's happening when we do this full Bayesian estimation. So we need to take into account everything. Every new covariance is just taking into account everything, right? And this is a little tedious. And actually, it's not just tedious, but it has some disadvantages. So it's great because, yes, we have the right distribution, but the price to pay is that we are considering always all cross terms, all relations, everything, right? Even doing some assumptions like this, like correlated noise, still we are always adding cross terms that are not zero. Okay, so, well, as I said, it's going to be the same, but just translated, and we can also write it this way, right? So this is x. Right, so play around a little. You see here, this is the transpose of this. Here, what I'm doing is just creating this rectangular matrix out of these blocks, and all of them are just multiplied by this Jacobian. Okay, so we see that this Jacobian actually it's very important. It's affecting almost all our covariances, right? And now I'm going to write. I'm going to write what is this new augmented. What is this new covariance after augmenting the augmented state. Okay, so these are known terms. Okay, and these are the new ones that we have just added. Oops. I didn't know I can move these things. So the first one that we calculated is this covariance of the new one, right? And we know that this is equal to the projection of our current state on X, I mean the covariance of the state on X, plus whatever observation noise we have, right? And this also we need to transform this with this Jacobian. Right, so this is this term here, right? And this makes a lot of sense because the covariance of this is going to be depending on how certain we are on our state. If we are not certain, if there's like a lot of uncertainty, we don't know where we are, then this landmark is going to be like not certain as well, right? So that's why this is directly directed. And then we have this term that this is just as far as we can go, right? This is the observation noise. This is basically every noise, every observation that we do, there's going to be some noise. So this Q can be bigger or smaller, but still here, if we have like height uncertainty on where we are, where is our state, where is this location, then this landmark, the initial estimation of this landmark is going to be not good, right? Basically, things are related. At the end, everything here makes sense. Now let's go for the cross terms. I have divided the cross terms in two parts, right? One was like this, so this is the cross term of X with respect to the landmark, right? So this makes a lot of sense. They are just related by this just linear transformation. And then we have the cross terms here, basically this multiplied by LT, right? And the same happens on these blocks on the bottom part of the matrix, right? So we'll have this, and here we have this. So you see, this covariance actually has a lot of structure. It resembles a lot our previous estimates, right? You cannot really come here and say, yeah, these are zeros, this is your new covariance, because if you do that, then your prior might be, yes, then your filtering might not work properly, right? You will not be considering these cross terms, and at the end, this gives you information. If you observe this new landmark, it's because you have this. When you do correction, these things that are related are going to affect one each other. So at the end, we want this kind of relations. If you see a landmark, and this landmark is connected to a previous state or to another landmark, this should improve like estimation of everything. That's why we do this simultaneously. If we break this down into two problems, different problems, and we don't care about cross terms, this is what happens. You do the best estimate, and then you fix like some distribution to be a given number, and then from there you start estimating things. That's not correct. What we do here is do the joint estimation of everything at the same time. So that's why we need all these cross terms here. That's a little the price to pay. It's a little tedious to derive this, but this, on the other hand, allows us to calculate simultaneously all these new landmarks, positions, and the positions of the landmarks. Okay, any questions so far? Yes. So you are talking, you start with a map of known landmarks, and then you will be adding new landmarks. If you don't have any prior knowledge, you could start with your belief being that this is a diagonal estimation. But you are going to see now in the correction that doesn't matter if your initial belief of landmarks is a diagonal, if they are independent. Because the moment that you start observing them from different positions in the correction step, which is the one that I'm going to explain now, there's going to be cross terms that are going to appear because you see the same landmark from different positions. And basically, this is creating a link, right, to all our poses. So it's actually a very interesting topic. And at the end, eventually, if you have an infinite trajectory, you observe all landmarks from all places. Even if you start with a sparse matrix, just being this the identity, this will be like a dense matrix. This is one of the problems of this kind of approach for EKF. You have a question? Yes, please.
Why don't we use, when you explain it, why don't we include the observation? So when you have a new landmark,
yes.
you start estimating with the predicted mean.
Yes.
Why don't you do the correction step with the landmarks involved, and then estimate everything with the correction?
So the question is, why are we, let's say, hallucinating this new landmark based on the mean of our observation and the mean of our state instead of just correcting? No? Can you repeat that? No, but it's important to initialize first the landmark. Okay, we will discuss it later then. Okay, so then let's go to the correction step. Right, and I see here, this is where all these cross terms are going to appear, as I have. Right, remember that here so far we are also considering correspondences, right? So this is something that I haven't used so far, but you always need to assume this. Okay, so we have discussed a little about this. This is a single observation at time t. Right? And then here what we are going to have is this augmented state. And then what we have is these correspondences. If we have correspondences, you agree that we just go into this vector, of this augmented vector, look for the right position of the landmark, and that's it. Right? So we have all we need, the robot position and the landmark position. Okay, and then we are going to add some noise. So we need to redefine this. We need to redefine this function now that we know that this is nonlinear, right? If you remember, there were like, well, some square root, some arctangent, all these things that are not linear. So what we are going to do is linearize, right? And just adapt this new function to the augmented state such that we can use in the extended Kalman filter. So this, it's always done by first order Taylor expansion. Here we have this function evaluated at the mean, right? This is the best place to start. And then we have here the Jacobian with respect to this state, right? So this is the Jacobian of our observation with respect to y. Okay, so let's go a little in detail. What is exactly this Jacobian? Because this is gonna be important, right? I'm gonna write it this way. Always Jacobians, the same methodology. We start here. We have here this. We have here the, well, this is actually not so important, but this is the correspondence. And then we derive with respect to augmented state, right? So as always, this is going to be first the derivative with respect to xt, right? This is going to be the derivative, let's say, with respect to m1. This is going to be the derivative with respect to all landmarks, right? Until we hit, let's say, our landmark j. This is the one that we have, it's given by the correspondence, right? So in this case, we know that the landmark that we are observing is j. And then we have a lot of other landmarks that are there. Okay, so, well, the first thing we know is that what's the relation of this observation function with other landmarks that we are not observing? Is that gradients should be non-zero, should be 0, right? If they are non-zero, basically it means that it doesn't matter how much you change these variables, but this function remains the same, right? So this is a way of saying that they are not affecting the result of. So gradients are going to be 0. It doesn't matter how much you perturb these values, right? So this is what the gradient is doing, small perturbations. It doesn't matter how much you change these landmarks because you are not observing them anyway, right? You only care about this j landmark here, right? So this is the only that it's going to be non-zero, right? While the others are just going to be 0. Okay, so then what we have now, I'm not going to simplify the Jacobian into lots of zeros that I'm not writing. I need the full vector, right? If you write like what is the Jacobian of what is the derivative of this is the derivative of the square root, right? I'm just writing for you to have it, but you can do the derivation at home if you want. Here, remember that Q was this sum of squares. I have defined it before. You can derive these Jacobians if you want later, but it's not really, it's not really part of the class. The class is understanding what do we do with these Jacobians, right? So you have them here, but you can calculate them. You can just use these derivations, whatever you want. It's not strange functions. They are actually. Okay, so this is the y position, y, and here we have the derivative of q. Just q. Q we have defined it before. Q is this. I defined it before, so it's just, well, long, well, this relative distance, basically, or the square of the relative distances. Okay, and then we have here the position of the landmark, position x of landmark x, of landmark j, minus x, q, and here we have a minus 1, right? So this is the derivative with respect to. And then what do we have here? So we are going to have a lot of zeros. until we get to this landmark j, which is going to be non-zero, and then the derivative with respect to landmark Okay, so this is now the derivative of j, of h, with respect to landmark 1. And now we know that this is important, right? Because it's basically affecting how much, well, the range depends on the two things, where the robot is and where the landmark is. So both for the range and for the bearing, it's going to be important. So that means that the Jacobians here are going to be non-zero. Okay, here, I don't have space. Okay, well, if you see on the notes, there's going to be the derivative with respect to y as well, but it's basically this with respect to y, and then here, this with respect to x is okay, so, and this is a large vector. We have a lot of other zeros here. Okay, so on the notes you will have this. Let me rewrite this a little more compactly. So then our Jacobian with respect to t, it's going to have the following way. So this is what I'm writing here. This is our old Jacobian that we described in lecture 6, right? We are just deriving this observation function. So that's what I'm writing it this way, h of x. We are going to have a lot of block zeros. These are not, I mean, these are matrices as well. And then there's going to be just one Jacobian, and I'm just going to write it this way, Jacobian with respect to j, because this is the landmark that is relevant for calculating this observation. And then there's going to be a lot of zeros, right? So then what do? We have everything, right? So if you go to the EKF correction, you just need to apply the formulas. It's nothing else. It's just obtaining the Kalman gain, updating the new mean, right, which is going to be affected by, well, whatever observations we got, and then the new observation, the new covariant, the covariance of this belief considering observation and action, it's going to be also multiplied by this Jacobian here. So it's just following the formulas. The only thing that we have done today is adapting all these functions, right, to be augmented, right? So we have augmented this state, we have augmented transition function, and now we have augmented observation function. We also need to account for new landmarks, and that's why we included like all this derivation, and actually that was a little more complicated than doing the correction step. Why? Because the correction step was already explained, so Kalman filter, it was already taking this into account. We were already discussing this a lot. The only thing we needed is to calculate these Jacobians. So once you have this, everything matches, dimensions are right, and then you just apply the algorithm. Okay, so this is it for today. Next, we are going to talk about data association. There's going to be some readings at Canvas. And if you go to probabilistic robotics, some parts of chapter 10, and I think 11, they talk about some of the things that we are going to be discussing on data association, but I would say that mostly take the readings at Canvas and class notes that I will publish today or tomorrow. Okay, see you all in Thursday.